So last time we defined the Alexandrov angle between two geodesics in a metric space, right? So what you do is you take two geodesics and you look at the points on them, C1t, C2t prime, for t prime tending to 0, and look at the comparison triangle in R2 formed by those 2 points and the common vertex, and take the angle there, and then take lim sup of the angle, right, as t prime tend to 0. So let me just show you the picture. Right, so here's the Alexandrov angle. It's the lim sup as t prime tend to 0 of the angle at P between C prime T prime in the model space of curvature 0, which is R2. So this angle P0QR, this denotes the angle at P bar in the comparison triangle P bar, Q bar, R bar, right? So what we're doing is we have two geodesics starting from a point P. We look at CT, C prime, T prime, and we look at the corresponding Euclidean triangle in R2, comparison triangle. And then we take the angle theta here. And this angle is defined to be this comparison angle, angle P0 CT C prime T prime. And then we take lim sup as T prime tend to 0 of this. Okay. So this is the Alexandrov angle between two geodesics. Okay. So, so we proved last time that it satisfies this property that the Alexandrov angle, if I take three geodesics, C, C prime, and C double prime, then it satisfies a sort of triangle inequality, right? The Alexandrov angle between C, C double prime is less than or equal to the Alexandrov angle between C, C prime and C prime, C double prime. Okay. So that's where we finished last time. So now I want to first make a remark that if C is a geodesic on an interval defined in a neighborhood of the origin, say from minus A to A into X. So if I look, so then it defines a forward geodesic, C plus of T is CT for T in the interval 0 to A, and a backward geodesic, C minus of T is C of minus T for T in the interval 0 to A, right? Then the angle between C plus and C minus is pi. Is this clear? The Alexandrov angle between C plus and C minus is pi because
lying in R2.
Because in R2 the triangle is a degenerate triangle, right? So if I have this is P and this is C of T and this is C of minus T prime, right? Then we have equality in the triangle inequality, right? This distance plus this distance is equal to this distance, right? So, so if I look at the comparison triangle, T bar C minus T prime bar CT bar, right? Then the distance between C minus T prime bar CT bar is equal to the distance between C minus T prime bar P bar plus P bar CT bar, right? But that implies that this angle theta is pi, right? So this is my triangle delta bar in R2. And this is my triangle delta in X. Is this clear? Yes?
Yes.
Okay. So the Alexandrov angle between a forward geodesic and a backward geodesic belonging to the same geodesic is pi. Similarly, if I take a geodesic and I take a restriction of it, okay, so then I get 2 points on the same geodesic. So then I have a picture like this, say CT prime CT, right? So in this case, I get this picture where I have P and CT prime bar, sorry, P bar, CT prime bar, and CT bar. So in this case, I have equality in the triangle inequality going this way. So the angle at CT prime bar is pi. Which implies the angle at P bar is 0, right? So therefore, this is delta bar in R2. This is delta in X. So this implies that the angle between C and C prime is 0 if C prime is a restriction of C, right? Is this clear? Okay. And above we have here that the angle between C plus and C minus is pi. So are these two properties clear? Yes? Yes, is this okay?
Yes, sir.
All right. Okay. So now we take these properties and turn them into an abstract definition of what's called an angle function in a metric space. So it's a map on pairs of geodesics with a common endpoint. C prime goes to A of C prime, which is in the interval 0 pi. So this is defined on pairs of geodesics with a common starting point such that it's symmetric. A C prime is A C prime C. It satisfies this triangle inequality. A C double prime is less than or equal to A C prime plus A C prime C double prime. And A C prime is 0 if C prime is a restriction of C. And if C is a geodesic on an interval around 0, then AC plus C minus is pi. Right? So the Alexandrov angle satisfies all these 4 properties, right? Okay. But this is not the only possible angle function. Depending on the metric space, so if X is a geodesic space, so it's also called the length space, then the Alexandrov angle satisfies these 4 properties. But you could also take a complete Riemannian manifold, and there you take A to be the Riemannian angle between geodesics. So that will also satisfy these four properties, right? The only property that you need to check is that this triangle inequality, right? So so the Riemannian angle in a manifold is an angle function So if I have three geodesics like this, so the Riemannian angle is just the angle between the tangent vectors, right? So say this tangent vector, so this is say C, and this
And
tangent.
by definition, sir, are we considering that it is always lesser equal to pi, right? This Riemannian angle?
Yes, yes. You take the angle in the interval 0 to pi, right? So, so here is a V, V prime, and V double prime, right? And the angle is the same. We can assume these are unit vectors, right? Okay. So if this point is P, then we have V. So this was C prime, and this was C double prime. So this is V, V prime, V double prime. These are unit tangent vectors. So these are in TP1x, right? And for unit tangent vectors, well, I mean, one way to see that you have the triangle inequality is, you see these points, they lie on a sphere, right? And in a sphere, this angle here is the same as, it's proportional to the arc length, right? From V to V prime along the geodesic in the sphere. Is that clear? Right? So this arc length here is less than or equal to the sum of these two arc lengths, right? Because this is a geodesic. So it's less than or equal to this length plus this length, because this is the shortest length path, right? So that means this angle is smaller than this angle plus this angle. Is that clear? Yes?
Yes, sir.
Okay. So that's it. So any questions? Is this okay? Yes, is this all right?
Which angle is smaller than what? What did you say? Just can you repeat?
So the angle from V to V prime, V double prime, this is the arc length of the geodesic from V to V double prime in the sphere,
Yes.
in the unit sphere, right? So this arc length is less than equal to the arc length from V to V prime and V prime to V double prime, right? Because this is the shortest length path.
Yes.
So therefore, the arc length from V to V prime is the angle V prime, and V prime V double prime is the arc length is the angle. So this angle is less than or equal to the sum of these two angles, right?
Yes. Yes.
Okay, so maybe let me just say it like this. So angle V double prime is equal to arc length or just length. I mean, let me just go. Why am I calling it arc length? So just length of geodesic in the sphere TP1x. So this is identified with Sn minus 1, right? From V to V prime, V double prime. This is less than or equal to length of geodesic V to V prime plus length of geodesic V prime to V double prime, and that is equal to angle V prime plus angle V prime V double prime. Okay, so the Riemannian angle satisfies this. It's an angle function. All right.
Yes, sir.
Okay, fine. So now we'll give in a while a characterization of cat kappa spaces in terms of angle functions. So first I want to give the following characterization. So suppose X is a geodesic space or a length space, then the following are equivalent, and kappa is always less than or equal to 0, I'm taking. So X is cat kappa. This is equivalent to, for any geodesic triangle delta PQR in X, and for any X in the geodesic QR, the comparison point X bar in the geodesic Q bar R bar. So this is in the comparison triangle. This satisfies the distance from P to X is less than or equal to the distance from P bar to X bar. Okay, so it's clear that 1 implies 2, right? I mean, the cat kappa inequality is that this inequality should hold for all points on the sides of the geodesic triangle in X, right? And here we're only requiring it to hold for a vertex and a point on the opposite side of the vertex. So this is a much smaller class of pairs of points, right? Okay. So here we have P, Q, R, and I'm taking an X here, and I'm taking the comparison triangle in M2 kappa, and I'm requiring that if this point is X bar and this is Q bar, R bar, P bar, then I want distance Px less than or equal to distance P bar X bar. Okay, is this all right?
Yes.
Yeah, so 1 implies 2 is trivial, right? And 3 is the fact that if I take this triangle PQR in X, and I take X in PQ and Y in PR, where XY are not equal to P, then the angle between xy, the comparison angle in the space of curvature kappa in M2 kappa between xy is less than or equal to the angle between QR in M2 kappa. Okay. So this, what is this saying? This is saying that comparison angles, they increase monotonically along geodesics, right? Here xy are moving along the geodesics PQ and PR starting from P, right? So this comparison angle is increasing monotonically as x and y move along the geodesics. Is this clear? Right? So this is equivalent to cat kappa, that the comparison angles increase monotonically. Okay. All right. So, okay, let me do the proof here. So, okay, so proposition. The following are equivalent. One, x is cat kappa. Two, if I have this picture, PQR, X, P bar, Q bar, X bar, R bar. This is delta in X. This is delta bar in X in M2 kappa. Then distance Px is less than or equal to distance P bar X bar. Okay. And 3, if I have this picture, P, Q, R, and I take a X here, and I take a Y here, and I then basically if I take two comparison triangles, so P bar, Q bar, R bar, and this angle is theta. And I take another small comparison triangle, P bar prime, X bar prime, Y bar prime, for the triangle PXY. Okay. So then I get another angle theta prime. So then I want theta prime less than or equal to theta. Okay. This theta prime is what I'm defining to be the comparison angle at P kappa XY. And this one is theta is angle P kappa QR. Is this clear? Right? Yes?
Yes.
Okay. So, so here let me draw X bar and Y bar here. These are comparison points for X and Y. So proof 1 implies 2 is trivial, right? cat kappa implies that you have the cat kappa inequality for all pairs of points in the triangle. This is only for particular pairs where you take a vertex and you take the opposite a point on the opposite side, right? Okay, so 1 implies 2 is trivial, and then 1 is equivalent to 3. This is easy because if I look in this picture, let me look at these two triangles, P bar, X bar, Y bar, and P bar prime, X bar prime, Y bar prime. So these have the same side lengths on these sides from P bar to X bar, and P bar prime to X bar prime, and P bar to Y bar, and P bar prime to Y bar prime, right? So mod P bar X bar, this is equal to distance Px, which is equal to mod P bar prime X bar prime and mod P bar Y bar is equal to distance Py is equal to mod P bar prime Y bar prime. Okay, right? So X is cat kappa if and only if distance xy is less than or equal to distance x bar y bar, right? But this distance xy is the same as the distance x bar prime y bar prime. So this is less than or equal to distance x bar y bar. And this inequality, this we saw that when you have two triangles in M2 kappa, which have the same side lengths starting from a common vertex, then the angles are less than or equal. One angle is less than or equal to the other, if and only if the opposite side is less than or equal to the opposite side, right? Yes, we saw this last time, right?
Yes.
So this is if and only if theta prime is less than or equal to theta. Okay, so that is if and only if this angle kappa p kappa xy is less than or equal to angle p kappa qr. Is this okay? Yes?
Yes.
Yes.
Okay. So what do we have to prove now? We just need to prove 2 implies 3. Okay, that will finish the proof, right? Because 3 implies 1 already we have here. So 1 implies 2, 2 implies 3, 3 implies 1. That will prove that they're all equivalent. So let's prove 2 implies 3, right? Okay. So what I do is I have my triangle here. I have to, and I'm taking 2 points x, y. I have to show the comparison angle between xy is less than or equal to the comparison angle between QR, right? Okay. So what I do is the following. I form, well, 3 triangles really. So one triangle is going to be a comparison triangle for okay, let me do this properly. So I already have my comparison triangle for PQR. So this is P. So I already have P bar, Q bar, R bar. Okay. Then I have a smaller comparison triangle. P bar prime, X bar prime, Y bar prime. Now I'm going to form a third triangle, which is going to be a comparison triangle for PXR here. Okay. So this, let me call this P bar double prime, X bar double prime, and R bar double prime. Is this okay? Yes. This should be Y bar prime. All right. Okay. So now what can I say? So here, if I look at in this last comparison triangle, I can take a comparison point for Y, right? So I get a point Y bar double prime. Okay. So this is my delta bar in M2 kappa. This is delta bar prime in M2 kappa. And this is delta bar double prime in M2 kappa. Okay. So now let me compare this triangle here with this triangle here. So you see P bar prime to X bar prime is the same as P bar double prime to X bar double prime, right? So P bar prime, X bar prime is equal to P bar double prime, X bar double prime is equal to distance Px. And similarly, P bar prime, Y bar prime is equal to P bar double prime, Y bar double prime is equal to distance Py, right? So again, I have two triangles with the same side lengths at the common vertex. So therefore, this angle here and this angle here, their relation depends on the relation between the opposite sides. But now I can use my hypothesis 2. So this triangle here is a comparison triangle, this delta bar double prime, and I'm taking a vertex, X bar double prime, and I'm taking a point on the opposite side, Y bar double prime. So therefore, if I look at the triangle PXR here, then the distance XY is less than or equal to the distance X bar double prime, Y bar double prime, right? Yes. And the distance XY is equal to the distance X bar prime, Y bar prime in this triangle. So mod X bar prime, Y bar prime is less than or equal to mod X bar double prime, Y bar double prime, right? That means that this angle is smaller than this angle, right? So therefore, I get that angle kappa PXY is less than or equal to angle at P bar double prime between X bar double prime and Y bar double prime, right? Is this clear? Yes? Right? Okay. Now this angle is the same as the angle at P bar double prime between x bar double prime and r bar double prime. Okay, but now in this big triangle p bar, q bar, r bar, I take the comparison point x bar and I look at this triangle x p bar, x bar, r bar, and so now I know again by 2, I know that in this comparison triangle, right, the distance from x to r is less than or equal to distance from x bar to r bar, right? So what does that give me? The distance from x to r is the same as the distance from x bar double prime to r bar double prime. So I get that mod x bar double prime, r bar double prime, this is equal to distance xr, that is less than or equal to distance x bar, r bar. So if I compare these two triangles, then what I get is that, again, these have the same sides at the vertex p bar and p bar double prime, the same side lengths here and here. So therefore, this implies that the angle, so if I look at the comparison angle, between, okay, so we've got less than a minute. So let me stop and let's start again. Okay, let me stop here.